In this episode, we're going to build a clear beginner mental model for virtualization on Linux, focusing on three ideas that show up again and again in Linux Plus style questions. What KVM and QEMU are, what VirtIO is, and why some virtual machines feel fast while others feel painfully slow. Virtualization can sound abstract at first because you are running a computer inside a computer, but the core concepts are practical once you connect them to resources you already understand, like CPU, memory, storage, and networking. Beginners often assume performance is either good or bad because of some magic virtualization setting, when the truth is that performance comes from how the virtual machine is presented to the guest and how efficiently the host can provide resources. We will keep this high-level and concept-focused because you do not need to memorize tool syntax to understand what the exam is looking for. If you can explain what role each component plays and what causes bottlenecks, you will be able to interpret virtualization scenarios without guessing. The point is to understand the architecture and the performance story in plain language. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Virtualization starts with the idea of a host system and a guest system, and the relationship is important because it defines who is borrowing resources from whom. The host is the real machine running Linux, and it owns the physical hardware like the processor, the memory modules, the disk, and the network interface. The guest is the virtual machine, which behaves like an independent computer but is actually a set of processes managed by the host. The guest thinks it has its own CPU, its own memory, its own disk, and its own network card, but those are virtual devices backed by the host's real hardware. This is why virtualization is both powerful and constrained. Powerful because you can run multiple guests safely and flexibly, constrained because every guest ultimately shares the host's finite resources. When you troubleshoot virtual machine performance, you are often really troubleshooting resource scheduling and device emulation on the host. Linux Plus questions typically test whether you understand that a virtual machine is not a separate physical entity. It is a workload competing for host resources. KVM is a key term because it represents hardware-assisted virtualization on Linux. Kernel-based virtual machine, KVM, is not a separate product you install as a standalone application in the same way you might install a typical program. It is a capability of the Linux kernel that lets the system use hardware virtualization features present in modern processors. The easiest way to think about KVM is that it turns the Linux kernel into a hypervisor-like layer, allowing guest operating systems to run with near-native execution for many instructions. Without hardware assistance, virtualization typically relies heavily on emulation and translation, which is slower and more complex. With KVM, many guest instructions can run directly on the physical CPU while still being controlled and isolated by the host. This is one of the big reasons KVM-based virtualization can be fast, because it avoids the overhead of pretending to be a CPU and software for every instruction. In exam terms, recognizing KVM as the kernel's virtualization support helps you place where the performance advantage originates. QEMU is another term that often appears right next to KVM, and the relationship between them is a common point of confusion. QEMU is a machine emulator and virtualizer in user space, which means it runs as a normal program on the host, but can provide the illusion of a complete machine. It can emulate different kinds of hardware, which makes it very flexible, including running architectures different from the host in some scenarios. However, pure emulation is slower because the host has to interpret or translate instructions and simulate devices and software. When QEMU is paired with KVM, QEMU typically provides the virtual hardware model and device framework, while KVM provides hardware-accelerated execution for the guest's CPU operations. In other words, QEMU is often the machinery that creates the guest environment, and KVM is the acceleration engine that makes running the guest practical and fast on the same architecture. Linux Plus questions frequently want you to see that KVM and QEMU are complementary rather than competing because they solve different parts of the virtualization problem. To understand performance, you need to understand where the work happens when a guest runs. Some parts of the guest workload can be executed efficiently with hardware assistance, especially CPU instructions that the processor can run directly. Other parts require the hypervisor layer to intervene, such as privileged operations, memory mapping, and interactions with devices. Every time the guest needs something that must be mediated, there is overhead because control shifts between the guest context and the host context. This is why virtualization performance depends not only on raw CPU speed, but on how often the guest forces those mediated transitions. Devices are especially important here because I/O-heavy workloads cause frequent interactions with storage and networking, and each interaction can create overhead if handled through slow emulation paths. The exam often frames this as why a virtual machine that seems to have enough CPU still feels slow, which is often an I/O and device path story, not a simple compute story. The mental habit is to ask whether the bottleneck is compute, memory, disk I/O, or network I/O, because each has a different virtualization cost. VirtIO is central to the performance story because it is a family of paravirtualized device interfaces designed to reduce the overhead of device emulation. Paravirtualization is the concept where the guest and host cooperate through a special interface that is designed for virtual environments, rather than pretending the guest is talking to a physical device that must be perfectly emulated. When a guest uses VirtIO devices, it can communicate with the host more efficiently, often using shared memory and optimized pathways that reduce the number of expensive transitions and the amount of emulation work. For beginners, a helpful way to think about VirtIO is that it is like using a fast, purpose-built virtual device driver instead of forcing the system to simulate an old physical device for compatibility. This can dramatically improve disk and network performance, because those are I/O-heavy areas where emulation overhead can be significant. Linux Plus questions that mention VirtIO are often pointing you toward the idea that the choice of virtual device model affects performance. If you remember that VirtIO is an optimization mechanism for virtual devices, you can reason about why enabling it matters. Now let's talk about where performance comes from in a more structured way, starting with CPU. With hardware virtualization, many guest computations can run close to native speed, but performance still depends on how the host schedules vCPU time across guests. If too many guests compete for limited physical cores, each guest may spend time waiting, which feels like slowness even if each guest has been assigned multiple virtual cores. Oversubscription is the idea of assigning more virtual CPU capacity than the host can provide simultaneously, which can be fine for bursty workloads but can hurt when all guests demand compute at once. Another factor is that certain operations still require hypervisor mediation, and frequent context switching can add overhead. The exam may describe a host running many virtual machines where everything becomes sluggish, and the correct reasoning includes contention and scheduling rather than assuming a single guest is misconfigured. In your mental model, CPU performance in virtualization is a mix of hardware acceleration plus host scheduling reality. Memory performance is similarly tied to how the host manages allocation and how the guest's memory needs are satisfied. A guest expects contiguous memory space from its own perspective, but the host is mapping that to real memory, and that mapping has to be maintained efficiently. If the host is under memory pressure, it may have to reclaim memory, which can lead to paging behavior that hurts performance, and that pain can be magnified because both host and guest may have their own memory management decisions interacting. Beginners sometimes interpret memory-related slowness as a CPU problem because everything feels slow, but memory pressure often shows up as delays, stuttering responsiveness, and heavy I/O. In virtualization, memory tuning and availability are often the difference between a smooth guest and a sluggish one, because memory shortages force expensive operations like paging to disk. Linux Plus questions may hint at this by describing that performance degrades when multiple guests run or when a guest workload grows, which can be a memory contention signal. The key concept is that virtual memory is real memory under management, not free magic memory. Storage is one of the most common virtualization bottlenecks because disk I/O is slower than memory and because virtualization adds layers. A guest sees a virtual disk, but the host is translating guest I/O requests into operations on a real disk or on a file that represents a disk image. Each layer can add overhead, and if the virtual disk uses an emulated device model, that overhead can be larger. This is where VirtIO shines, because a paravirtualized disk interface reduces the work needed to handle each I/O request. Another factor is the storage backend itself, such as whether the host storage is fast or congested, and whether multiple guests are competing for the same physical disk. If many guests do heavy I/O at once, the host storage becomes a shared bottleneck, and everyone slows down. The exam often presents symptoms like a guest that boots slowly or a database guest that performs poorly, and the correct reasoning often includes storage path efficiency and contention. In your mental model, storage performance is a blend of device model, host backend speed, and shared contention. Networking performance has a similar story because the guest's virtual network interface is backed by host networking and virtual switching. The guest thinks it has a network card, but sending a packet involves the guest stack, the virtual device, the host mediation layer, and then the host network interface or virtual bridge, depending on the setup. If the guest uses an emulated network device, the overhead can be high, while VirtIO network devices can reduce overhead significantly by offering a more direct and efficient interface. Networking also depends on the host's ability to process packets, which can become a bottleneck if many guests are producing traffic. Another subtle point is that virtual networking can introduce additional latency, even when throughput is high, which can affect certain applications more than others. Linux Plus questions might not demand deep virtual networking design, but they may ask why a guest network feels slow, and the answer often involves device choice, host load, and the number of layers between guest and wire. The conceptual takeaway is that network I/O is not free. It is processed by both guest and host. Another important contributor to perceived performance is the difference between raw speed and responsiveness, because users often care about how quickly a guest reacts rather than the maximum throughput. A guest might have enough average compute capacity, but still feel laggy if it is frequently paused while the host services other guests or handles heavy I/O. This is why oversubscription can feel worse than you expect. Even if the host can eventually provide enough cycles, the timing of those cycles matters for interactive workloads. Similarly, storage latency can make a system feel slow even when throughput is acceptable, because small waits add up across many operations. The exam sometimes describes scenarios where a guest seems to have enough resources allocated but still performs poorly, and the right reasoning is to consider contention and latency in shared resources. Thinking in terms of bottlenecks and shared queues helps you interpret those scenarios. Performance in virtualization is often about avoiding the slow path and reducing contention, not just about increasing assigned resources. By the end of this episode, you should be able to describe KVM as the Linux kernel's hardware-assisted virtualization capability that allows guest execution to be accelerated using processor features. You should be able to describe QEMU as the user space component that provides machine and device emulation, and that often pairs with KVM to create a full virtual machine environment with efficient CPU execution. You should be able to describe VirtIO as a paravirtualized device framework that improves performance by reducing emulation overhead for disks and networks, and by enabling more efficient guest-to-host device communication. Most importantly, you should be able to explain where performance comes from by thinking in terms of CPU scheduling, memory availability, storage I/O path efficiency, and network I/O path efficiency. When a scenario describes slowness, your first response should be to identify which resource is the bottleneck and whether the guest is using an efficient virtual device path. That mindset is what Linux Plus wants you to demonstrate. Understanding of system behavior, not memorization of slogans.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.